This is Rosen, section 5.3 on recursively defined sets and structural induction. Here we start our discussion of recursively defined sets. To have a set that is recursively defined, you must have some sort of basis. That set is what is in the initial collection. And then we will apply a recursive rule to give a recursive step to give rules for forming new elements in the set from those that are already there. In general, we apply the exclusion rule that the only thing that will be in our sets are those that were either there at the basis or were created using the recursive step. We may not always mention the exclusion rule, but we will assume it even if it's not mentioned. And then later we'll develop a type of induction related to mathematical induction called structural induction to make some proofs about recursively defined sets. Let's look at some examples. All right, so here we're building up a set where the basis is 3. And the recursive step says that if x is in the set and y is in the set, then the sum is in the set. So for the first step, initially, the only thing that's in S is 3, but then 3 plus 3 equals 6 is in S, and then 3 plus 6 equals 9 is in S, and so forth. And you can see that what we're doing is building up a set that contains all the multiples of 3. A rather more straightforward one would be the natural numbers. Here we say the basis step is 1 is in n. And then if the recursive step is if lowercase n is in n, then lowercase n plus 1 is in n. I note that this deviates from the author's assertion in other chapters that 0 is also an element of the natural numbers. So initially 1 is in S, and then 1 plus 1 is equal 2 is in S, and 2 plus 1 equal 3 is in S, and so forth. And we'll come back to the set S that's producing multiples of 3 and do a proof about that. First, let's look at a couple more examples. Here we have a set of strings. Sigma star is a set of strings that uses an alphabet that's contained in the set sigma. And we define it recursively as we start with lambda, which is known as the empty string. We say that it is in the set of strings. And then recursively, we say that if W is in our set of strings and X is a symbol in our alphabet, then W appended with X is also in the set of strings. And here's an example of if my alphabet is 0 and 1, what are the set of strings? Well, it starts with alpha in the basis step, and then 0 and 1, then 0, 0, 0, 1, 1, 0, 1, 1, and so forth. If our alphabet is the set containing A and B, we can show that AAB is in the set of strings. First, we start with the empty string and we append the empty string with an A to get A in the set of strings. Then since A is in the set of strings and A is in the alphabet, then A appended with A is in the set of strings. Finally, since AA is in the set of strings, B is in the alphabet, AAB will be in the set of strings. Balanced parentheses, we can give a recursive definition of the set of balanced parentheses. What that means is parentheses that are open and closed in a balanced way. The basis step is an open and closed parentheses that is in our set. And then if W is in our set, then I can create balanced parentheses by putting a pair of parentheses to the left of W, around the W, and to the right of W, where again, W is an element of my balanced parentheses. All right, we want to show that this set of parentheses is in P. How would we do that? Well, we could start with our basis case, and then append parentheses to the right of it, and then enclose that with parentheses. And this would not be in P because we can see that there's no closure of those parentheses, and this one would need something over here. So there's no way we could get that using our rule. We can also define well-formed formulae in propositional logic recursively. We have propositional variables, usually lowercase letters, truth and false values, and all of our logical connectives. And we say that the true value and the false value are in our basis step in all propositional variables. We say that they're well-formed formulae. And the recursive step is that new well-formed formulae can be formed from those already in the set by negating it, conjoining it, disjoining it, putting it into a conditional or a biconditional relationship, and we include the parentheses for this purpose. So in this case, this would be a well-formed formula because P, Q, Q, and F are well-formed. Then P or Q is well-formed, Q and F is well-formed, and then finally the conditional statement between those two is well-formed. And I think you'll be able to see that that is not well-formed because the conjunction operator cannot occur without something on both sides. All right, let's use induction to prove some things about recursively defined sets. Let's go back to that set S, which was built up from 3 being in the set and the basis, and then x plus y is in S whenever x and y are in S. We want to prove that that is a set of all positive integers that are multiples of 3. So we'll let A be the set of all positive integers divisible by 3. We want to prove that they're equal, and we're proving two sets are equal. We want to show A is a subset of B, A is a subset of S, and S is a subset of A. So we'll start with A as a subset of S. So A contains multiples of 3. That means anything with 3 times an integer will be in A. Pn is a statement that 3n belongs to S. We want to prove that's true for all n. We'll use the basis. We'll use induction. So at the basic basis definition for S, 3 is in S, and 3 times 1 is 3. That comes from A. So the basis step is true. Now we assume pk is true, that 3 times k belongs to S. And the second part of our recursive definition for S is since 3k is in S, then 3k plus 3 is in S. But that equals 3 times k plus 1, which is the statement pk plus 1 is true. All right, so A is a subset of S, and everything that looks like 3 times n belongs to S. Let's show that S is a subset of A. All right, so that is everything built up by the recursive definition is a multiple of 3. All right, so 3 is an element of S, and 3 is divisible by 3, so S is a subset of A after the basis step. For the inductive step, we want to show that X, the second part of the recursive definition, okay, so remember that X plus Y is in S whenever X and Y are in S. We're going to assume that X and Y are in A, anything produced before the current application of the recursive definition. Then 3 times X and 3 times Y are, then 3 divides X and 3 divides Y. And since x plus y will be divisible by 3 since each of them are divisible by 3. X plus y is also in A. So we used mathematical and strong induction and leveraging the recursive and basis definitions for the set S to prove a result. And later in this chapter, we discuss a different type of induction that leverages the recursive definitions directly.